Okay, I'm going to talk about the two things that I said you got to have for a generator. And the first is what I call magnetic neutralization. And we're just going to take a look at a rotor from the side view. So here's the side view of the rotor. There's magnets they don't really stick out from the rotor, but I'm going to show them as sticking out from the rotor on this drawing. And this is one way of doing it. And what I have here is two sets of magnets, one out at the rim of the rotor and one farther in. And they go, if you looked at the rotor in this view, there'd be magnets out here on the rim, and there would be bigger magnets in here that are going to go by the coils. Okay, so these are the ones that line up with the coils. And here's the coil, and I have a coil on each side of the machine. That's the core of the coil sticking out, and then the coil itself with all the winds on it. Okay. Now the idea is, as the rotor goes around in a circle, and I'm going to erase this for a second. Let's just say this is the magnet on the rotor, and it's going to come around past the core of the coil. That makes sense. Okay, as this magnet goes past the coil and aligns right over the top of it, there's another magnet on the rotor that aligns with a magnet out at the rim. So what I have are magnets right here and right here. Not quite so big. And these magnets are adjustable in and out. Actually, let's put arrows on both ends, so in and out. And what happens is, the magnet wants to attract to the iron core of the coil, and it wants to attract to this iron core, but this magnet, these two magnets, are in repulsion. So as this attracts, this repulses, and it creates a place of neutralization where the magnets on the rotor are neither attracted nor repelled by the coil cores, and so the rotor just freewheels. It spins with no magnet, what I call magnetic drag. And the difference is that my motor, running on 36 volts, consumes 1.3 amps when it is running just all by itself, not turning a rotor. When it's turning a rotor with no coils in place, it consumes 12. When the magnetic neutralization is in place, it runs on 36 volts at 12 amps. Without these magnets, right here, and this one, without these magnets in place, I wrote these numbers in the wrong place. You're not even going to be able to see them. Okay. 36 volts at 1.3 amps. That's with nothing, no rotor, nothing on it. Just that's what it runs on. 36 volts at 12 amps with the magnetic neutralization magnets in place on the rotor. Without them, when it's just like this, and there's 12 coils in the stator and 12 magnets in the stator and 12 magnets on the rotor and 12 coils in the stator, It consumes 36 volts at 29 amps. Okay, 36 volts times 29 amps is really close to 1,000. Can't write down that far and have you even see it. 1,000 watts just to run it. Where 36 volts is 12 amps is about 400 and something watts, not much over 400. So it makes a big difference to have that magnetic neutralization in place. It's the key to getting your machine to run for as little cost as possible. Now the second key to getting your machine to run for as little cost as possible is the phenomenon known as speeding up under load, or delayed lens. I don't like to call it either of those things. I look at it more as outrunning lens, because here's what happens. As the magnet approaches the coil core, there's three things that happen. One, there's a magnetic field around the magnet that starts to interact with the core of the coil. So that's the first thing that happens on a timeline. Okay, it begins to interact. The second thing that happens on the timeline is the flux begins to accumulate. Now, actually we're going to draw it like this. The flux begins to accumulate in this core. Okay, so that's the second thing that happens on the timeline. The third thing that happens on the timeline is electricity begins to be generated in the wires of the coil if it is attached to, say, a light bulb. That's a really great drawing of a light bulb. If it's attached to a light bulb as a load. Oh. Let's put our drawing of our light bulb down here so it's actually on the camera. Okay, so here's our light bulb. Okay, so that's the third thing that happens, is it starts to generate electricity. The fourth thing that happens is enough electricity is accumulated in the windings of the coil to turn the coil into an electromagnet that repels the approaching magnet. Okay, but if at the time that you're waiting for all this to happen, this magnet has moved to where it's right here over the top of the coil, before all these steps can take place, then there is no repulsion created that pushes the magnet away before it approaches, because it's already there. It's just a matter of timing. You can outrun lens. It depends. There's three conditions. The first one is, there's three ways you can do it. Number one is that you have the speed of the rotor. If it's fast enough, the coil will not have a lens reaction in time to repel the approaching magnet. Number two is the capacity of the coil. You can get a difference in capacity by the way you wind the coil, and that's Tesla's patent. Okay, that tells you how to wind a high capacity coil so that it takes longer for it to fill up with electricity. The third is the core. The core has to fill up with the flux before it is able to start inducing that field in the wires that create electricity. So if the core of your coil is way out here, the flux is even throughout the core, and only part of it has the windings on it, so it takes a long time for the flux to accumulate enough in the core that it induces the reaction that you want in the windings. Lens is not a law. Lens is a reaction. It's a reaction that takes place when these things happen. When a magnet approaches the core of a coil, the steps that I outlined take place. And if you can delay those steps until the magnet that's approaching has reached top dead center, all of a sudden it becomes an electromagnet the coil becomes an electromagnet that pushes the approaching magnet away, but it pushes it away in the direction of rotation. And so it's a lens assisted motor. You don't want that to happen with a generator coil, because the more assist that coil gives, the less it produces as a generator coil to your load. So what you want is a lens neutral reaction. You want the timing to be such that it doesn't speed up, it doesn't slow down the motor. The motor maintains a steady rate of RPMs, and the generator puts out the maximum amount of power. And that's the way you make this thing work to your best advantage. Those are the two things you need to know to get a generator that will output more than it takes to make it run.